Hi, I'm Kalinga Nirasha Ishani Vimalananda and my index number is MS24908542. This is the video presentation of the assignment of the Wireless Network Technology module, and in this presentation I'm going to cover what I've learned from this module from lecture 1 to lecture 6. And I'm going to cover the fundamentals of wireless and data communication, advanced signal concepts, network protocols and security challenges, and wireless LAN and security. So let's get begin discussing foundation knowledge required for wireless communication. So introduction to wireless networking. Wireless networking serves as the backbone of our modern digital infrastructure. It's what enables our smartphones, laptops, IoT devices, and countless other technologies to communicate without physical connections. This technology has transformed numerous sectors from telecommunication and healthcare to finance, smart cities, and industrial automations. So, connectivity essential for telecommunication and smart cities enables smart cities, and that is very popular among people. Industrial automation facilitates automation. And today's presentation will cover the fundamentals of signal transmission, network protocols, security mechanisms, and emerging trends that will shape the future of wireless communication. Understanding these concepts is crucial as we become increasingly dependent on wireless technologies in both professional and personal contexts. So, the fundamentals of wireless and data communication. Let's start with the basics. All wireless communication relies on signal properties that you see here, like frequency, amplitude, phase, and bandwidth. So, frequency refers to cycles per second measured in hertz, while amplitude measures the signal intensity. Phase indicates the displacement of a signal wave relative to time zero, and bandwidth represents the range of frequencies used. So, a key concept to understand is the difference between analog and digital signals. So, analog signals are continuous waves from waveforms that can take infinite values. Think of a radio waves. Digital signals, on the other hand, we are are discrete waveforms with defined high and low states, represented as 1 and zeros. So the digital signals always represent in 1 and zeros, and digital signals offer greater resistance to noise and interference, which is why most modern communication systems use digital technology because it is more effective and reliable. Signal measurement and processing. So when working with signals, we need accurate ways to measure them. So this is where decibels come in. The decibel, we can represent it in D and simple D and capital B, is a logical unit that expresses the ratio of two power values. For power gains, we use the formula that represent here, and we can calculate the power gain by calculating this formula. While voltage we can calculate using the next formula that represent here. And also another crucial measurement is the signal to noise ratio, or SNR. This ratio compares the level of the desired signal to the level of background noise. A higher SNR means better signal quality and fewer errors in data transmission. So this concept is fundamental in designing reliable wireless system that can operate in noisy environments. So we can measure this SNR in also decibels. Advanced signal concepts. To transmit digital information over analog channels, we use modulation techniques. So there are three common methods that we use. So one is amplitude shift keying, known by ASK, which modifies the amplitude of a carrier waves. And then the other one is frequency shift keying, is FSK, which varies the frequency to represent binary values. And then phase shift keying is known as PSK, which changes the phase to encode data. So, and there's another thing called Shannon capacity. So there's a formula. So the Shannon's capacity formula is a groundbreaking concept that defines the theoretically maximum data rate achievable in a noisy channel. So the formula C equals B log 2 1 plus S divided by N shows that the C depends on the bandwidth B and signal to noise ratio in S divided by N. So this formula helps engineers to optimize optimize bandwidth allocation and design effective communication systems. And then let's move on to multiplexing. So multiplexing is how we efficiently utilize communication channels by combining multiple signals for transmission over a single medium. There are several approaches. So in frequency division multiplexing is known as FDM, we assign different frequency bands to different signals. This is commonly used in radio broadcasting. And then when it comes to TDM, which is known as the time division multiplexing, so this allocates different time slots to signals. This is widely used in digital telephone networks. And the other one is FDM, the wavelength division multiplexing. This applies the FDM concept to fiber optics using different light wavelengths for different signals. And the other one is CDM, known as code division multiplexing. This assigns unique codes to signals, allowing them to share the same frequency band. This is the foundation of CDM in mobile networks. And let's move on to the digital hierarchies. So in telecommunication, we organize digital signals using hierarchical structures. The order plesiochronous digital hierarchy, which is known as PDH, handle multiple data streams with slightly different clock frequencies requiring complex synchronizations. So the modern system use synchronization digital hierarchy, the SDH, which employs a signal clock preference for precise synchronization. This enables enhanced multiplexing, higher data rates, and better performance in optical fiber networks. The shift from PDH to SDH represent a significant advancement in telecommunication infrastructure. And let's move on to antennas. So it's a really common thing for everyone in the world. So antennas in wireless communication is something like this. Antennas are essential component that convert electrical signals into electromagnetic waves and vice versa. They are the bridge between our devices and the wireless medium. So wavelength propagation from antennas to follow specific patterns with waves radiating uniformly. So the polarization refers to the direction of the electric field component in the electromagnetic wave. And for optimal signal strengths, transmitting and receiving antennas should have the same polarization. Antennas comes in various forms and sizes, depending on their application, from the tiny ones in our smartphones to satellite dishes, and their design is specifically tailored to the frequencies they operate with, whether it is Wi-Fi, cellular networks, cellular communications, or broadcasting. And let's move on to the analog to digital conversion with PCM. So, converting analog signals to a digital format is crucial for modern communications. So, the process known as pulse code modularization, which is known as PCM, this involves 3 steps. So the first one is the sampling. Sampling takes the measurement of the analog signal at a regular intervals. So according to the Nyquist theorem, we must sample the least twice as fast as the highest frequency component to accurately reproduce the original signal. And then next, the quantization, it approximates the sample to the nearest predefined level, introducing some error. And then finally, encoding converts these quantized values into binary code that computers can process. This technique forms the basics of digital telecommunication and radio application, allowing us to process, store, and transmit information with high fidelity. So let's move on to multiple access technologies. So when multiple users share a communication medium, we need protocols to manage access and prevent chaos. Random access or continuation-based methods allows stations to transmit whenever they have data, but this can lead to collisions. The Aloha protocol was the earliest random access method developed at the University of Hawaii. While it didn't prevent collisions, it established procedures for retransmission after collision occurs. This pioneering work laid the foundation for modern collision handling techniques. So about the CSMA, CSMA is the Carrier Sense Multiple Access. So in this the Carrier Sense Multiple Access improves upon Aloha by implementing the listen before talk principle. So the devices check if the medium is busy before transmitting. Significantly reduce but not eliminating collision. In In wired networks, we use CSMA-CD collision detection, which detects collisions and triggers retransmission. This was the foundation of traditional Ethernet networks, though it is less relevant in modern switch networks. For wireless networks, we use CSMA-CA collision avoidance, which aims to prevent collisions rather than simply detecting them. It employs request to send and clear to send RTS or CTS messages to coordinate access to the medium. This approach is necessary because detecting collision is much more difficult in wireless environments. So, IEEE 802 standards. The IEEE 802 standards define how networking devices communicate. These standards separate the data link layer into two sublayers, the logical link layer and it's known as LLC. This sublayer handles error checking and flow control, ensuring data integrity and reliability across the network. And then the media access control, the MAC, sublayer regulates how devices access the network and uses MAC addresses, uniquely identifiers assigned to network interfaces for device identification and communication. This layered approach allows different network technologies to interpret seamlessly, which has been crucial to the development of heterogeneous networks. TCP/IP protocol suite. So, the TCP/IP protocol suite is the foundation of the Internet and most modern networks. It follows a layered architecture. So there are three layers: application layer, transport layer, and network layer. So the application layer provides services directly to end users such as web browsing and email. The transport layer ensures the reliable data delivery between endpoints. The network layer handles addressing and routing packets across networks. The data link layer controls access to the physical medium. The physical layer manages the actual transmission of raw bits. As data moves down this stack, each layer adds its own header, a process called encapsulation. This structured approach simplifies network design and troubleshooting by separating concerns and different levels of the communication process. So let's discuss about the TCP/IP versus UDP comparison. At the transport layer, we have two primary protocols with different characteristics. TCP or Transmission Control Protocol establishes connection before transmitting data and ensures reliability through acknowledgement and retransmission. However, this reliability comes at the cost of increased overhead and latency. So I have written down some of the TCP/IP related points: connection-oriented, guaranteed delivery, error checking, and slower transmission. And then it comes to the UDP or user diagram protocol is connectionless and doesn't guarantee delivery. It is simply send packets without waiting for acknowledgements. While this makes less reliable, it's also faster and more effective for applications where occasional data loss is acceptable, such as video streaming or online gaming. So the choice between TCP and UDP depends on the specific requirements of your application, whether you prioritize reliability or the speed, because UDP is connectionless, faster transmission, minimal overhead, and no guarantee of delivery. And then let's move on to wireless LANs. Wireless LAN or wireless local area networks uh, typically use an infrastructure-based approach where access points connects wireless client to wired network backbone. The basic service set, the BSS, consists of a signal AP serving clients with its range, while an extended service set ESS uses multiple interconnected APs to cover larger areas and enable seamless roaming. Two common problems in wireless network are the hidden terminal problem, where two stations can detect each other but both communicate with the same AP, and the exposed terminal problems, where a station unnecessarily differs transmission. These issues are addressed using RTS over CTS handshaking mechanism. So there are several wireless standards. The IEEE 802.11 family defines various Wi-Fi standards, each with different characteristics. So the first one, 802.11a, operates in the 5 GHz band and offers speed up to 54 Mbps. And 11B uses the 2.4 GHz band with speeds up to 11 megabits per second. And then 11G also uses the 2.4 GHz but increased speeds to 54 megabits per second. 802.11n operates in both bands and introduce MIMO technology for higher throughput outputs. So the AC, the last one, focused on 5 GHz with very high throughput capabilities. Each standard represents an evolution in wireless technology with improvements in speed, range, reliability to meet growing demands for wireless connectivity. Wireless network security. Security is paramount in wireless network due to their inherent vulnerabilities to eavesdropping and also unauthorized access. Several security protocols have evolved over time. So the WEP, the wired equivalent privacy, was the first attempt at securing wireless networks, but proved weak and easily compromised. The WPA, the Wi-Fi protected access, improved security with stronger encryption methods. The WPA the further enhanced protection by implementing the Advanced Encryption Standard AES. And then the the latest protocol the WPA3 offers the strongest protection yet, with improved resistance to brute force attacks and forward secrecy. Best practices includes using strong passwords, enabling strong available encryption, and keeping firmware up to date to patch security vulnerabilities. These measurements are essential for protecting sensitive information transmitted over a wireless network. And then, wide area networks. When connecting to device over long distance, we use wide area networks or WANs. Unlike LANs, which typically use dedicated cabling, WANs often leverage existing infrastructure like telephone networks or the internet. Data transmissions across a WAN involves multiple stages of encapsulation and de-encapsulation as packets move between different network types. This process starts with the client connecting to local router via LAN protocols and router-to-router communication using various WAN protocols, and finally delivery from the destination router to the server. So each link in this chain maybe uses different technologies and protocols, requiring careful translation between them. So then the client-server model. So most network applications follow the client-server model where programs running on different hosts communicate with each other. The server process provides services while client processes request them. Servers can be either iterative, handling one client at a time, or concurrent, which is managing multiple clients simultaneously. So the connection between clients and servers can be either connection oriented, where a session is established before data transfer, or connectionless, where data is sent without prior connection establishment. Connection oriented approach offer reliability but with higher overhead. With connectionless methods are faster but less reliable. So I have here represent the communication and the iterative servers, the concurrent servers, and connection types in the client-server model. And then the error control mechanism. So ensuring data integrity during transmission is critical. Two primary approaches are automatic repeat request ARQ, which detects errors using techniques like cycling redundancy check, CRC, and request retransmitting when errors are found. And then the forward error correction FEC, which adds redundant bits to the transmitted data, allowing the receiver to detect and correct errors without requesting transmission. These mechanisms work at various layers of the network stacks to ensure end-to-end integrity, which is essential for reliable communication. And then, and the conclusion, the wireless network has become an indispensable part of our connected world, enabling unprecedented mobile and convenience. So the principles we discussed today form the foundation of technologies that we use. So in the future in looking forward, several trends are shaping in the future of wireless communication, such as 5G is already there. Network are dramatically increasing speed and capacity while reduce latency, and the AI machine learning are optimizing network performance and security, and also the Internet of Things is connecting billions of devices, creating new possibilities and challenges. Enhanced security protocols are evolving to counter sophisticated threats. So, despite remarkable progress, challenges remaining the main managing network uh, congestion and ensuring security. As we continue to depend more heavily on wireless technologies, addressing these challenges will be crucial for building resilient, high performance networks. Thank you for your attention. I'd be happy to be here today um, to explain what I've learned from this module from lecture 1 to lecture 6.